worst. -1. Okay. Today, section 12.3 is going to cover the dot product. Let's quickly go over some of the basics of the law, or the law of cosines of the dot product. We're going to define a new vector operation, which is going to be something like, but not necessarily multiplication. In fact, we're going to look at two different ways of multiplying vectors together. So it turns out that just saying multiply two vectors isn't enough on its own to really specify exactly what we mean. So we need to create ourselves a new operation. And that operation is going to come from our desire to figure out the angle between two vectors, drawn over here on the right. I just drew two vectors, A and B, put the angle theta in between them, that's in green, and then filled in some other pieces that I thought I was going to need. In particular, that third vector C across the top, this sort of completes my triangle. So you can see I have a triangle involving vectors A, B, and C. I'll just treat them as if they're in space, creating a triangle. And I wanted to figure out C in terms of A and B. So from the tip of B, I subtracted A, which should complete a parallelogram. Since I know that those two sides, A and -A, are parallel to each other. And yeah, that's all I really need for that parallelogram, right? Same length, they're parallel to each other. So those other two gray lines ought to complete my parallelogram, meaning that C has a measure of B minus A, or vector C at least is equal to B minus A. Through that, I'm going to go back to the law of cosines from trigonometry, since that's my other major course, is trigonometry. Might have been why they picked me for Calc 3, I'm not really sure. But either way, law of cosines, which says that c squared is equal to a squared plus b squared minus 2ab cosine theta, or cosine c, is maybe how you've seen it from that trig class. It's basically the Pythagorean theorem, but for non-right triangles. And if we do a whole bunch of math that I'm going to gloss over because it would take the rest of the class period, I get this result at the bottom. A1, B1 plus A2, B2 plus A3, B3 is equal to the magnitude of A times the magnitude of B times the cosine of the angle between those vectors. So the thing on the left, A1, B1, A2, B2, A3, B3, that's an important enough calculation that we're going to give it a name. And that thing is going to be the dot product. So we could say that the angle between our two vectors is that sum, where, didn't really define it yet this morning, so we'll do it again, right? Do that right now. A1, A2, and A3, where I'm giving those subscripts or those indices to the letter A. Those are all used to represent the component of the vector A. So A1 is just the first component of the A vector. A2 is the second component of the A vector. A3, third component, so on like that. So when we're usually using X, Y, and Z, that'll correspond to A1, A2, and A3. Same thing for vector B. Also, I want to point out again that whenever I want to talk about a vector value specifically, I'm going to be putting a hat on it. So all of those A's, B's, and C's that have the hat on the top of them mean that they're a vector. And then when I start talking about its components, like A1, A2, and A3, those are now all scalar values. Those are just numbers. So I don't have the hats on the little numbers anymore. So A1, A2, A3, B1, B2, B3, none of those get hats because they aren't vectors themselves. They're instead the scalar components that make up my vectors. So again, I'll do my very best to make sure that I have a hat on every single vector quantity that I want to talk about. Hopefully I stay consistent with that. So again, we define our dot product as that fancy product that we found in trying to find the angle. Oh, don't fail me already. Yeah, okay. And again, that bit that I talked about, where we use A1, A2, and A3 to represent the components of a vector. So one important element to note about that dot product is that when take those two vectors, take their dot product, which is A1, A2, A1, B1, A2, B2, A3, B3, my result is a scalar value. Right? I'm just adding those three products together, but they result in a single number. So just a scalar value. So a dot product takes two vectors, multiplies them together in some way, and then the result of that dot product is a scalar value, only a number and not a vector. That'll be important as we, use this stuff in various contexts. And we'll also see that the next version of multiplication for vectors does not result in a scalar, but more on that next week. But as long as the dot product is 0, then the vectors are perpendicular because that means the angle between them is 90 degrees, since the cosine of 90 degrees is equal to 0. But right, enough of all that. The new stuff. We did that in second. Not too bad. So the angle between two vectors is given by the thing that we already found, but maybe written a little bit more elegantly, is that the angle between two vectors is the cosine inverse of the dot product divided by the product of their magnitudes. We don't have to write out A1, B1, A2, B2, A3, B3 every single time we want to talk about dot product. We'll just write it as the dot product. Called the dot product because we use a dot to indicate a product. Yeah, real fancy. Also, in case it's been a minute since you've seen the inverse trig functions, arc cosine and cosine inverse mean the exact same thing. So they'll be used interchangeably. Same thing with sine inverse and arc sine, or tangent inverse and arc tangent. Same function. So just, as a reminder, both of those notations will work. So if we want to find the angle between a pair of vectors, why don't we go at that? I'll just want to take the dot product of A and B, which is 1 times -1 plus 0 times 3 plus 1 times 2. And I'm pretty sure that's 1. I think even I can add those numbers together. So to get that angle, a little bit bigger, that angle should again be the arc cosine of A dot B. Making sure to put my hats on both of those, divided by the magnitude of A times the magnitude of B, which looks like the cosine inverse of 1 divided by the square root of, looks like 2 for A, and the square root of 14 for B. If anybody has a calculator and wants to tell me what that angle is, I would be much obliged. While someone out there works on that, I got that 2 and that 14 by taking 1 squared plus 0 squared plus 1 squared is 2. And then 1 squared plus 3 squared plus 4 squared, 2 squared, excuse me, 1 plus 9 plus 4, and that's 14. So anybody find arc cosine of 1 over root 28? No one? I think it's about 0 point. Nope. That's not going to be it. All right, fine. I'll go pull out a calculator. Somebody got it already? I'll take it either. You said 79? 79.1 degrees. Sure, we'll take that. Most of the time, I think we're going to be doing angles in radian measure. But if it's like an exam question, I know we'd take it either way. But web work, I'm pretty sure the quizzes are specifically in radians most of the time. And I know if you just type in the arc cosine function into web work, it's going to assume that you wanted radians. So we got that one in degrees, but we'll get the next one in radians just to switch things up. So if I need A dot B on this next set of vectors, I'm going to be looking at 1, -1, 3, dotted with 0 to 4. So that dot product looks like 0 minus 2 plus 12, which I think comes out to 10. And then I want the arc cosine of 10 over a pair of square roots. That first looks like it'll be square root 11, 9 plus 1 plus 1. And the other guy, 16 plus 4, that's square root 20. And once again, somebody's got a solution for me. I would be much obliged. I mean, don't be shy now. You've seen me screw up math worse than this before. Say again. 0.83. How about two more decimal places? 0.9. Perfect. Mark that in radians. Hopefully that number's correct. If it's not, blame that guy. But we're gonna call it close enough for now because past that, I'm not gonna be too worried about what happens once you get a calculator involved. As long as your method's good, we'll be pretty happy. So let's come over and look at a few properties of dot products. I worked on this one ahead of time, but I could have some more time to go over some interesting ideas. But to quickly cover some of the elements that are here, the dot product itself, I rewrote down what it was. We have the associative property. So I should say a couple of things about vectors versus scalars here. I suppose I kind of already did that earlier, but why don't I specifically mark off some of those extra bits in gray to further emphasize when I'm talking about a scalar instead of a vector, which means, well, let's just grab is that gonna work? It is gonna work. Cool. We'll keep our operations. Cool. So I filled in all of the scalar values in gray just to further emphasize I'm talking about only a number. This is talking about a vector. Just in case the hat wasn't specific enough, those are now in gray when they're scalar values. So in part B, where I've got CA dotted with B, that's just a scalar multiple going into that vector A at first. But then I have pretty sure that's the associative property. I don't remember what they're all called. I just remember what they do. That says I can move that scalar from one vector to another. So I don't think we commented on it specifically, but if I multiply a vector by a single scalar, say by 2, to take my vector A, multiply it by 2, that's going to be equivalent to just multiplying each component by 2. All right, so if I'm multiplying a scalar into a vector, I just multiply that scalar value onto all the components of whatever that vector is. So the associative property holds just like we know from algebra. We'll go over the next one, which is the distributive property. So if I want to take the dot product of a vector with a sum of vectors, I can just distribute that vector to both of the individual guys. those individual vads. If I multiply, if I take the dot product of 0 and a vector, I get 0. Notably, that 0 over there is the 0 vector instead of just 0. Those two things are going to look an awful lot alike. The 0 vector is just a vector where every component is 0. So if we're in 3 space, that's 0, 0, 0. I can only take the dot product of two vectors that have the same rank. Don't quote me on that word. But the two vectors need to have the same length, right? So if I've got a vector in 3 space, I can only take its dot product with another vector in 3 space, meaning each vector must have the same number of components within them. So if I want to take the dot product of 0 and A, then I need 0 to have just as many components as A does. So if I'm in 3 space, you got to multiply my 3-component A vector with 0, 0, 0 in order to get the dot product. And finally, if I take the dot product of a vector with itself, my result is the square of its magnitude. So that magnitude already is the square root of a bunch of square terms. So if I get the magnitude squared, then I just get rid of the square root part. And it's just the sum of the square terms that are normally underneath that radical. So it's a1 squared plus a2 squared plus a3 squared. But to look at a rough outline of the proof for how that distributive property works, I just brute force it until it worked. So I know I can add two vectors together. B plus C is going to be B1 plus C1, B2 plus C2, B3 plus C3, PO. And then tried to collect my terms as best as I could. So I highlighted my B and C components with purple, yellow, and magenta for the first, second, and third components of that vector. And then I thought that was a little bit helpful to try to track my numbers through the problem. Because once it became regular old multiplication, I just got to do the multiplicative distributive property for scalar values, numbers. And then I just rearranged all of my terms in the second to last step so that all of the B's ended up on the left, while all of the C's ended up on the right. And then I can see that's just the dot product for A and B plus the dot product for A and C. In case you wanted to see that all out. If you're here in lecture right now, probably easier to just take a picture than write the whole thing down because that'll take about 5 to 10 minutes. And I'd rather move on. Because there's some more exciting things that we got to get to. But not before talking about a physics concept real quick. At least back from a physics 1 or a pre-calculus-based physics. If we just wanted to look at the work done by a constant force. Emphasis on constant there. So if you've taken the more fun levels of physics, put a pin in that for now. We'll get to it later. For now, we're just going to work with introductory physics. Work is force times distance. Just the product of those two things together. Again, as long as we've got a constant force. And that is how we did it back when we had scalar values, meaning we just had numbers, some force in newtons, some distance in a unit of our choice, but usually meters. But if we represent that force and that distance as a vector, instead of as just a scalar, then the work done by that force over that distance is just the dot product of those two things together. So I think force and displacement both make a lot of sense as vector values, since a force needs to be given a direction. So if you're familiar with the acceleration due to gravity, that always points down, which means we usually build weight off of gravity. Mass times acceleration also points down. If I wanted to shove this desk over there, Hopefully this isn't too loud. Oh God, that's heavy. I had to exert a force going that way in order to make it happen. Sorry for anybody watching the video because you didn't get to see that, but I shoved a really heavy desk over to my right and then pointed in that direction. So right, force and displacement, I think both have directions associated with them. I can exert a force in a direction, and displacement is just a change in position. So I can start somewhere and end somewhere else. The line connecting those two things is going to have a direction as well. Work, however, doesn't make sense as a vector. Work is just a value. Work is a measurement of energy, and energy doesn't have direction. It's just a scalar. So while force and displacement, I think both make a lot of sense as vectors, work does not, which is good because the result of a dot product is a scalar. There we go. So let's look at a new example. We have a constant force of 123 newtons. How much work is done in moving the box from 101 to 211? Well, I should calculate a displacement vector, which means I want my initial, no, try again. I want my final point minus my initial point to find that displacement. So I'm going to want 2 minus, nope, no comma, 2 minus 1. There we are. 1 minus 0 and 1 minus 1. Just write down the line, subtract the first point from the second point, which gives me a resulting vector of 1, 1, 0. I can also just confirm that by adding 1, 1, 0 to 1, 0, 1 and see that I get 2, 1, 1. So that's my displacement vector. That's where I'm going to move the desk over that way. Notice that the z component is 0 at the end because I didn't try to lift that remarkably heavy table. I just tried to shove it. So I want the work, which means I'm after the dot product of 1, 2, 3. Well, let me write out the formula. Force dotted with displacement, which is 1, 2, 3. Dotted with 1, 1, 0. And I get a result of 1 plus 2 plus 0, which is 3. I was given units in the problem, so I should probably put units on this answer. What units belong here? Here are some votes for joules, which I think ought to make sense, right? Joules are the standard unit for joules are the standard unit for work and for energy in our SI system. Work can also be expressed in Newton meters, if you feel fancy about that. But this was actually a trick question. And by trick question, I mean it was a poorly worded question. Because we have Newton distance units as our unit for energy here. Poorly defined problem didn't tell us what displacement system we were working in. So maybe if we redo these notes sometime, we'll say something about how these coordinates are given in meters, so that you actually could have a unit there. Fortunately, this is a math class instead of a physics class, so that isn't quite the cardinal sin. It would be in a different course. Still kind of didn't feel great about it when I solved this out, though. So, yeah. Maybe better to just leave units off of that problem. All right, the real fun one. Getting into projections. That's the second half of today's unit. So, a projection of one vector onto another one. which means we maybe want to define what a projection is. So let me just try some words first before I start working on diagram. So there's a projector in the back of the room, right? It's currently shining my notes on the projector screen. And our idea of a projection is going to have something to do with how a projector works. Effectively, I want to find some image by maybe projecting light onto an object and figure out what its image looks like, right? Because the image, the image of these lecture notes being projected on the screen isn't going to be the same as the notes that are originally being projected. The object that I want to project onto the screen won't look exactly like this. For starters, this projector screen is way bigger than my computer, which I'm using to project the thing. They're also way bigger than the projector lens in the back. This analogy is a little bit falling apart because that projector is doing some magnification in order and some focusing to project this image onto a screen, but kind of the same idea. I'm going to shoot some light at an object and I'm going to figure out what its image looks like. That's what we want a projection to be. And because we want to do this as nicely as possible, we're going to project at right angles because it seems like it would be a little bit chaotic to not do that. So my goal, I'm going to do projections in both directions for these two vectors, but I'm going to start by projecting u onto v. So let me just move my ruler a little bit. See, there's vector v there. I'm looking at the left. And b is at a 34-degree angle with the horizontal. So if I'm going to project u onto v, I want a perpendicular projection. I want to be projecting that thing at v onto v at a right angle. There we go. So in order to do that, I'm going to need the complement to 34, which I believe is 56. Just rotate my straight edge to 56 degrees. And go look at my initial and terminal point for u and draw in those perpendicular lines. Wah, 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 wah. Cool. So I've got those lines right there. Let's go pretend I actually have this physical light source somewhere. I don't know. What color is a good light source? How about orange? Cool. So there's my light source. I'm going to be shining it down this way. And so then the projection of u onto v is going to be this vector right there. Right? That's my projection. If I shine a light on u so that it's perpendicular to v, it's v dead on. My projection of u is just that element goes in the direction of v. So when I'm projecting a vector onto another one, the result should be parallel to the vector I'm projecting onto. And we're going to write this guy out as the, let's see if I've got space right here, the projection of u onto v. So the vector being projected onto is going to go in the subscript of our mathematical way that we're going to write this guy out. And then the thing that is being projected is the input into that function. If I look at that thing the other way, right, projecting v onto u, well, I'll do something similar, but this time I want to project onto u, which means I'll start by measuring its angle. It's at 83 degrees to a horizontal, so its complement is going to be 7 degrees. And it looks like I did get the correct 7. Love that for me. And again, I'll go draw in a couple of lines. Sound effects are incredibly important when you're drawing vectors, just as a heads up. Your classmates are going to love me when you're taking an exam. Right, let's throw in that same light, that projector we were using earlier. Be a little bar light hanging out up here. I'm going to project V onto you, so my light's going to shine out this way. Probably not going to draw that projector in every time, but it is fun for the first couple. So my projection ought to be that guy right there. That's my projection of V onto you. Projection of V onto you. Now, whose brilliant idea it was to use U and V as names for vectors? Don't really know. It is often rather difficult to distinguish a U from a V, particularly if I'm writing fast. I'll try my very best to keep those distinct, but if you ever have any questions about my handwriting, so maybe it doesn't look as good as it ought to, just stop me and ask, and I'll try to fix it. I think that mark was errant up there. That projection over here. So look at that. A couple of projections. Or looking at two vectors, I'm looking at the two natural vector projections that I might have with those lads. And one thing that I think is worth pointing out right away is that these two projections are not the same. Right, if I looked at projecting U onto V, and then I looked at projecting V onto U, and I got two different results. Maybe I should further emphasize that by giving this a color. How about red? So the order that we do a projection in matters. So we got to make sure that we get that right. Make sure that the vector being projected onto is paid attention to. So definition 3.10. We want the vector projection of B onto A. Gets denoted by that thing right there. Projection of B onto A. Again, the onto vector is the subscript, the one that is built into the function itself. And then it takes an input of some other vector. But we need to do something about that. And effectively, I want to break this down into two ideas. Since vectors have a length and a direction, I want to express my projection as those two pieces individually, a length and a direction. Starting with, well, what do I want to? Let me just jump ahead to what the answer is, and then I'll work my way back to getting there. The projection of these two things is going to be A dot B. Let me actually back that up. B dot A. I want to write it out that way. B dot A divided by the magnitude of A. That's going to be the length of that vector. I'll come back to do more on that in a moment. And I'm going to multiply that into my A vector divided by the magnitude of A. So that's going to be my projection. It'll look like this stuff all right here. Let me just change all of this A, all that A stuff into gray. Hey, come on, cut that out. So that my subject vector over here, B, only ends up getting used once. So a length, which I want to be the thing on the left, multiplied into a direction, the thing on the right. Separate those two things out for a moment. The thing on the right, I think, makes more intuitive sense. I don't want to talk about that first. That is simply the unit vector in the direction of A. Unit vector. Unit vector in the direction of A. Come on, come back here. So I took my vector A, divided away its magnitude so that it's only giving me a direction as a magnitude of 1, meaning when I multiply that unit vector into that length, it doesn't change the length of it at all. And also notice in that length, which I'm going to come back to arguing about in a minute, that length also divides away the magnitude of A. Right? In both cases, I'm dividing away the magnitude of my direction vector. Because when I go back to look at my projection, the thing I'm projecting onto, its magnitude, its length, shouldn't matter to me at all. The only thing I care about with that onto vector is its direction. I don't want its length to change the value of my projection at all. When I was trying to set up the length of that thing, when I was figuring out how long my yellow line should be, the only thing I was measuring were the initial and terminal points of U, of my blue vector, the one I've highlighted in blue over here. Let me just draw this guy in blue to, again, emphasize the 2 bits I'm talking about. That blue vector for B, kind of the color scheme I'm going to be using here, blue for B. When I tried to figure out the length of my yellow vector, the blue vector was the only one that mattered. So at every opportunity that I have, I'm going to divide away the magnitude of A, my projecting onto vector. And if we go to talk about where that bit comes from, no, I'm still going to hold on to that for just a second. We'll move that on to the component element. So let me just write down one other thing that I wanted to just have collected here. This is the component of B along A. That guy. But after I spent all that time talking about this form, the thing I really want to do is simplify it a little bit. This thing is really, I'm going to use some copy and paste technology. I managed to not copy my fraction bar, so let's add that back in. If I were to simplify that expression, best I can, dot product I've got to leave alone, but my denominator, I'm just multiplying the magnitude of A twice, so I can do the magnitude of A squared. And then all of that gets attached to A. All of that gets attached to A. Yeah, there we go. So if I just draw myself a little box, there's probably the formula that I want to use most of the time. I think it's a little I don't remember the individual pieces as well in its final form. I think it's a decent enough way to start. I can see here that my results of this projection is a vector that ends up going in the direction of A. Right? It's just some multiple, some number, right? Because the dot product results in a scalar, just some scalar multiple of A, my resulting vector. Hi there.
So, go back up a step.
Yeah.
So, you know the projection of U like onto B
Yep.
will always be smaller than B, or is it constant?
Gotcha. So the question was, when I'm projecting U onto V, will it always be smaller than V? Is it always going to be smaller than the vector I'm projecting onto? And no, that won't always be the case. For a first demo example, it was really nice to just have them fit within the vectors we're projecting onto. But we're going to see in a minute that really won't be the case. The length of the vector we're projecting onto should be completely irrelevant to the problem. Or at least it should be completely irrelevant to the result. But the calculation ends up needing it quite a bit because we need to keep dividing it away. Anytime we bring in our projecting our onto vector, we want to make sure that we're getting rid of its magnitude so that we're only taking its direction. Right, the components of that stuff, or the scalar projection, which we're going to call the component, that is just the thing that I think is already attached to our clipboard. I'm going to paste it again. Yep. It's just this part. So when I come back to my first definition for the projection of the first bit that I wrote out, the component, or the scalar projection, the length of the vector that ends up over there is just the coefficient. It's just the multiple that gets attached to the unit vector, that b dot a over a. And then I just want to go talk about some other stuff from an older version of my notes, because I thought there were still a few other nice things in here. Just a separate sketch for if that helps you visualize it at all. And lets me also talk about, this is also let me talk about over here, where that component comes from. Actually, I had the elements over here that I wanted. Looking at my vectors all put together here, I'm projecting A onto B, so the letters are backwards from what I just did, but hopefully that's fine. Just think about projecting the blue vector onto the gray vector. Looking at my new projection, which is the yellow vector I've drawn in, same as I did with the other example, that blue and yellow vector form a right triangle, or at least, a natural right triangle. I just need to add in the third side and it'll be all right there, which means I already know how to calculate the length of that other vector. It's just that new vector is just my original blue vector times the cosine of theta. It's its adjacent side. So the length of C, the length of my projection, should be the length of the vector that I care about, the magnitude of that vector multiplied by the angle in between those two vectors. And we already had an expression for cosine theta. And it's the dot product divided by those two magnitudes. But I also need to multiply the length of the vector I care about back in, multiplying the length of that blue vector back in, which is where that A dot B divided by just the magnitude of the vector I don't care about comes into play. From here, yeah, it's the same fun thing that we did all right there. So we have a second definition for the scalar projection, or the component, involving an angle, and also re-emphasizing that the projection order matters. I can't reverse the direction of A and B and still get the same results. So let me add in back here. This is also equal to the magnitude of my blue vector, the one that I care about, times the cosine of the angle between them. All right, I've got 4 minutes to cover a few more examples. I might have suspected I wouldn't get through everything today. So consider the two vectors u and v. I want to project u onto v. So u, grab my ruler over here. Kind of an angle are you at? 31 degrees, sure. So that's going to be u right here. V then is the angle going the other direction. I need to actually not have done that angle. I want this one. 37 degrees. Yeah, looks about right. I'm going to draw in the line that V sits on, because V is, again, that guy. The angle that's complementary to 37, I believe that's 53 degrees. Hey, stop that. So my projection is going to be just this little guy over here. Hey, stop that. That's my projection, the little yellow vector drawn in right there. So as I might notice just by sketching out the projection, not only did we say that the length of the vector I'm projecting onto shouldn't matter, my projection could also end up going in the opposite direction, which will happen if the angle between our two vectors is greater than 90 degrees. And if those two things come past 90, the projection is going to go over the back end of the vector that I want to be onto. And that's totally fine. Projections will work like that. So if we want that projection, I'll call it C. It's just this guy right here. I need the dot product of u and v. So u dot v looks like negative 20 plus 9, which will be negative 11. So that projection vector ought to be, what did we say here? We want the dot product of u and v to go up top. That's negative 11. I want the magnitude of my onto vector squared. So my onto vector is v. That's what I'm going projecting to. 4 squared plus 3 squared, I think, is 25. Right, 16 plus 9 be 25. And I want that to be in the direction of v. So negative 4, 3. So that would be my projection. All told, I'll probably leave it factored because I think it works a little bit nicer that way. And then if I just want the component of u in the direction of v, that thing is going to be just negative 11 over the square root of 25, which is 5. Cool. Now, the part that I'm not going to be able to cover today is the orthogonal projection. So I'll just lightning round that thing real quick, because it's pretty easy once we've done everything else. So here's my set of projections. A being projected onto B is that yellow vector C. And the orthogonal projection is just the part that completes the triangle we were talking about earlier, which means the best way to write it out is that orthogonal projection is just my original vector minus the regular projection. Cool. More on that next week. Okay, bye, 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 bye. Bye, bye, bye. Bye, 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 bye. Bye, bye.